Hello students, welcome back to next session in unit number 3, that is the steam jet refrigeration system, where it is also one of the unconventional type of refrigeration system. So far we have seen these topics, and now we are going to see steam jet refrigeration. It is also known as ejector refrigeration system. We have completed vapor absorption and adsorption cooling systems. Now we are starting steam jet refrigeration system, and then in next session we are going to start thermoelectric refrigeration, and then we are going to start air refrigeration, and we have to discuss magnetic refrigeration system, vortex tube refrigeration system, pulse tube refrigeration system. So these are the left out topics in this unit. We will be discussing those in coming sessions. So steam jet refrigeration system, also known as ejector refrigeration system, is one of the oldest methods of producing refrigeration effects. So this is very ancient type of refrigeration method. And basic components of the system: evaporator, it is a device where the refrigerant absorbs heat and undergoes phase change. And compression device, a steam ejector or booster compresses the refrigerant to the required pressure level. So that is the compression device. It is obviously compressor. And we have condenser. A refrigerant is condensed back into a liquid form. Refrigerant control device, it regulates the flow and amount of refrigerant used in the system. So these are the four major components in steam jet refrigeration system. Steam jet refrigeration system's functionality is: the system uses steam ejector or booster, it is also known as booster, instead of mechanical compressor to compress the refrigerant to the required condenser pressure level. So a steam ejector is used instead of a compressor. So that is the replacement of compressor here. Refrigerant used in this system is water, and freezing point of water is 0 degrees Celsius. So this system is not suitable for applications below 0 degrees Celsius, and applications are widely used in food processing, such as cooling vegetables, concentrating fruit juices, and we have other similar processes also used in gas plants, breweries, and paper mills, etc. So principle of steam jet refrigeration system. So boiling point of water is, it is in normal conditions, pressure exerted on the surface of the liquid is the atmospheric pressure, and the boiling point of water under standard atmospheric pressure is 760 millimeter of Hg. It is nothing but mercury, is 100 degrees Celsius, and the boiling point of water can be reduced by decreasing the pressure on the surface of the liquid as follows. So the first, water boils at 12 degrees Celsius when the pressure on the surface is 0.014 bar at 7 degrees Celsius. The reduced pressure on the surface of water is maintained by throttling the steam into the jets or nozzles. So temperature reduction is achieved like this. The principle of cooling is based on evaporating water at reduced pressure. When the water is cooled from 10 degrees Celsius to 5 degrees Celsius, it absorbs heat by evaporating due to the reduced pressure in the evaporator. So here, when the water is cooled from 10 degrees Celsius to 5 degrees Celsius, it absorbs heat by evaporating due to the reduced pressure in the evaporator. So compression mechanism here in this system, steam jet refrigeration system, the system employs a steam ejector or booster to compress the refrigerant water to the required condenser pressure. So the operation allows the refrigerant to undergo phase change, that is evaporation taking place and effectively in the evaporator. So water is used here as refrigerant, and the role of water as refrigerant is water is used as refrigerant in the steam jet refrigeration system due to its availability to absorb heat during the vaporization. Latent heat of vaporization, so that is another characteristic or property of water, and water has a high latent heat, so meaning it can absorb substantial amounts of heat while evaporating. So mathematical representation here, M is mass of water in the evaporator, that is in terms of kg. HFG is latent heat of vaporization at some reduced pressure, and QR is heat removed from the water in terms of kilojoules. The amount of heat removed during evaporation can be calculated as QR equal to M into HFG. So if 1 kg of water is evaporating by throttling steam through the nozzle at a reduced pressure of 0.085 bar, let the mass of water M equal to 100 kg and latent heat HFG equal to 2400.5 kilojoules per kg at the reduced pressure. The total heat removed can be calculated as delta TF equal to 2400.5 into 100 minus 100 divided by 100. It is 5.577 degrees Celsius. So this calculation suggests that after evaporating of 1 kg of water, the temperature of the remaining water drops by approximately 5.577 degree Celsius. So this is the inference from this calculation. And temperature limitations are, since water has a freezing point of 0 degree Celsius, this system is not suitable for applications where temperatures below 0 degree Celsius are required. So it is not suitable for all the cases. So cooling process, the cooling effect in the system is achieved by continuous evaporation of water which absorbs heat from the surrounding environment. The phase change from liquid to vapor provides the necessary cooling. So the phase change is necessary. It is the phase change from liquid to vapor provides necessary cooling. So that is the phase change role here. And formula for temperature drop delta TF. So that is the temperature drop of the remaining water after evaporation is calculated using the following formula. So delta TF equal to QR by M, so that is a mass, HFG into M divided by 100, where delta TF is temperature drop in terms of degree Celsius, QR is heat removed in terms of kilojoules, and HFG is latent heat of vaporization at reduced pressure kilojoules per kg. M equal to mass of evaporated water, so that is in terms of kg. So working of steam jet refrigeration system. So I will show you one diagram. So from this it will be more clear, and this is the diagram. So here this is the pump, and it is a cyclic process. So chilled water coming from here, and pump is receiving that, and we have a refrigerated space, and that is sprayer is used to spray the water here, and chilled water is kept in this flash chamber or evaporator. So this is the evaporator, and warm water is coming from here, and now ejector is placed here, and nozzle is placed here, and this is going to boiler, and boiler is connected to the condenser, and this is the condenser. From condenser the makeup water is taken out here, and the warm water that comes here, that goes to condenser, and this is the makeup water pump. So that is removed, makeup water is removed from condenser, and a pump is used to remove that, and you see this is a cyclic process only. So this is cyclic process happening here. So working of steam jet refrigeration. So main components of steam jet refrigeration system, the flash chamber. So it is also known as evaporator, a large vessel. So that is shown in the diagram in earlier slide. A large vessel that is highly insulated to prevent heat gain, and it should be a insulated chamber. It is fitted with perforated pipes for spraying water. The warm water coming out of the refrigerated space is delivered into the flash chamber, where it absorbs latent heat and turns into vapor. So now phase change is happening here in this chamber, flash chamber. So next we have steam nozzle. So these steam nozzles, high pressure steam from the boiler passes through these nozzles to entrain the water vapor. So the water vapor is actually entrained here in steam nozzles. Condenser, the vapor is condensed in the condenser where heat is removed, and the flash chamber, the flash chamber or evaporator, it is also known as evaporator, is where warm water is sprayed and evaporated. The water absorbs latent heat, which results in production of vapor that helps cooling the surrounding water. The high pressure steam from the boiler is passed through the steam nozzles, increasing steam velocity and helping to entrain water vapor from the flash chamber. The steam and water vapor mixer then passes through the ejector, where it is compressed to a low pressure. So here the steam and water vapor mixer then compressed here in this chamber. So ejector and compressor, the steam ejector acts as the compressor here. So the role of steam ejector is more or less compressor in our conventional system, where the steam velocity causes a pressure drop, creating a vacuum. So this vacuum entrains the water vapor from the flash chamber. The water vapor mixer is then compressed and directed into the condenser, where it is cooled back to a liquid state. So again the phase change is happening here. And a pump is used to supply makeup water to the flash chamber and ensure a constant water level for the system. And you note here that the jet steam jet refrigeration system works under reduced pressure conditions. So that is the reduced pressure conditions, and where the steam pressure is low enough to allow evaporation of water at low temperatures. So this helps cool the surrounding water as it absorbs the latent heat from the vaporization. So this is a important note from the system. And when the chilled water from the flash chamber is directly used in the form of spray for cooling the air, then it is known as open cooling system. So open cooling system, what is open cooling system? It is one of the important 2 mark questions. And when the chilled water is passed through the coils and it does not come in contact with the cooled air to be cooled, then it is known as closed cooling system. So this is another closed type cooling system and open type cooling system. So these two are two important 2 mark questions. So this is the steam ejector, and steam inlet is through this nozzle, and this is the steam nozzle, and this is nozzle plate. Nozzle plate is provided here. It is the cut section of the nozzle steam ejector, and this is diffuser, and this is suction chamber. So this is suction chamber to the nozzle, and this is diffuser throat, and this is the discharge flap, and this is the cut section of steam ejector, very simple in construction. So steam ejector function, the steam ejector is an essential component of the steam jet refrigeration system. It acts as the compressor for the system, and it is more or less equal to compressor in conventional system for the system driving the entire refrigeration cycle. So steam ejector is playing such an important role here. High pressure steam, often referred to as primary fluid or motive steam. It is also called as primary fluid or motive steam. So this is high pressure steam from the boiler enters the steam ejector and expands through a nozzle, resulting in an increase in steam velocity and a decrease in pressure. So its design, if you see, the nozzle throat is designed to ensure that the steam exits at a high velocity up to 1350 meters per second. The nozzle is designed for the lowest operating pressure ratio between the nozzle throat and exit. The steam flows the steam flows through the convergent divergent nozzle, and where the velocity increases as pressure decreases. Of the system inefficient at high velocities. So this is not efficient at high velocities. So the process of steam ejector, the steam ejector mixes the steam with the entrained water vapors and the flash chamber. From the flash chamber, the high speed steam helps pull water vapors from the ejector. Once mixed, the steam and vapor flow through a diffuser where the velocity is reduced and the pressure is increased, thus compressing the mixture before it is sent to the condenser. So here the compression process is taking place before the condenser process. Design considerations: the nozzle pressure ratio should ideally not exceed 200, as this leads to poor performance of the ejector at low steam pressures. So we have to ensure that it should not exceed 200, the nozzle pressure ratio. The function of the diffuser is crucial as it helps slow down the steam mixer to ensure efficient compression. So we have multi-stage ejector also. In some systems, multi-stage steam ejectors are used to improve efficiency, allowing for a more gradual increase in pressure and reducing the risk of system inefficiencies at high velocities. So this is the multi-stage ejector. So analysis of steam jet refrigeration system, the temperature entropy TS diagram and enthalpy entropy HS diagram. So this is temperature entropy diagram. So here H are evaporator, and this is the points E, C and F, and this is the condenser temperature, and this is the motive steam temperature. So this is motive steam temperature, and that is the point A, and we have the flash chamber temperature or H or evaporator temperature, and entropy for corresponding points are given here. So this is temperature entropy diagram. So TS diagram shows the process of expansion and compression of steam in the ejector system. The point A represents the initial condition of the motive steam before passing through the nozzle. So this is the point A, and it represents initial condition of the motive steam before passing through the nozzle. And point B represents the final condition of the motive steam after expansion, assuming isentropic expansion here. And point C represents in the initial condition of water, the flash chamber evaporator before mixing with the steam. So point E shows the condition of the mixture of high velocity steam and water vapor after mixing. So point F shows the condition of the mixer after the ejector compression before being condensed in the condenser. So these are all the points and its significance. So temperature entropy diagram, enthalpy entropy diagram. So this is enthalpy and entropy diagram. So this is the HS diagram depicts the enthalpy and entropy changes during the expansion and mixing of the steam with water vapor. The expansion of the steam in the nozzle results in a decrease in the pressure and an increase in velocity, causing the steam to entrain the water vapor. So after mixing, the steam mixer undergoes compression, represented by a rise in enthalpy and a decrease in entropy, making it suitable for condensation and condensation in the condenser. So important points to remember here are isentropic expansion is happening here. This refers to the process where no heat is lost to the environment and entropy remains constant. This condition is assumed in the theoretical analysis of the steam ejector. So actual conditions are due to unavoidable losses in the expansion and compression processes. The actual expansion and compression paths deviate slightly from the ideal isentropic curve as shown in the diagram. So important points to remember from this: the steam jet refrigeration system relies on high pressure steam to compress the refrigerant water, which absorbs latent heat as it evaporates in the flash chamber. The steam ejector acts as the compressor, entrains the water vapor and compresses the mixture before condensed in the condenser. The system operates efficiently under reduced pressure, allowing the cooling in various industrial applications like food processing and breweries. The TS and HS diagrams are vital tools for analyzing the thermodynamic processes within the system, helping to optimize the design and operation of steam ejectors and other components. Efficiency is used in steam jet refrigeration system. So nozzle efficiency. So it is nozzle efficiency is defined as the ratio of the actual enthalpy drop to the isentropic enthalpy drop of the motive steam passing through the nozzle. So mathematical expression. So this is the mathematical expression, and eta n equal to Ha minus Hv divided by Ha minus Hb, and where Ha is actual enthalpy drop and Hv is the isentropic enthalpy drop, and the nozzle efficiency generally varies between 85% to 90%. So nozzle efficiency is very high and it is recommended. So efficiency is used in steam jet refrigeration. Next is entrainment efficiency. It is defined as the water vapors formed in the flash chamber or evaporator come out with a very low velocity as compared to velocity of the steam, and that is V coming out of the nozzle. So formula here: V equal to root of 2000 Ha minus Hr. So that is equal to 44.72 Ha minus Hr. So Ha is enthalpy of steam, Hr is enthalpy of vapor in the flash chamber. The entrainment efficiency may be around 65. So this is lesser than the earlier one. This process is called entrainment of the water vapor. So it is also a 5-mark question or a 2-mark question. So next is compression efficiency. The compression efficiency is the ratio of the isentropic enthalpy increase to the actual enthalpy increasing during the compression. So its formula is very simple: Hg minus He divided by Hf dash minus He, and Hg is enthalpy of mixture of steam and water vapor. He is enthalpy at the end of the compression process, and compression efficiency typically ranges from 75% to 80%. So mass of motive steam required, and here the conservation of energy. According to the law of conservation of energy, the available energy for compression should be equal to the energy required for compression, and formula for available energy compression: that is M into H minus A divided by HA minus HB equal to M steam plus M water into HF minus HK, where M is mass flow rate of motive steam and HA and HB are enthalpy before and after compression, and HF and HG equal to enthalpy of water at different stages. So energy balance, by using energy balance principles, the mass of motive steam required for the system can be calculated as M motive steam into efficiency, that is N into HA minus HB equal to mass of water into HC minus HK, and where M motive steam, that is nothing but the mass of motive steam required, and HC and HK are enthalpy values at various states of the system, and mass of motive steam per ton of refrigeration is equal to, from the above equations, the mass of motive steam required per ton of refrigeration is derived as, the formula for mass of motive steam required is Rg equal to M motive steam into Hc minus Hk divided by K, where Rg is refrigerating capacity, and M motive steam equal to mass of motive steam required. The coefficient of performance, so that is, this is the main efficiency of the system. Is crucial metric for assessing its efficiency, and COP equal to M motive steam divided by M motive steam into HC minus HK divided by HA minus HB. So this is the standard formula to measure COP, where HA, HB, HC, HK are specific enthalpy values at different points in the system. So efficiencies, the nozzle efficiency, entrainment efficiency, and compression efficiency play significant roles in overall performance of the steam jet refrigeration system. The efficiencies are essential for optimizing the energy usage and improving system performance. Mass of motive steam is equal to the mass of motive steam required for efficient refrigeration is calculated using principles of energy conservation, and specific enthalpy values ensure that the system operates within the least amount of steam maximum refrigeration capacity. So these are the 2 points. One more point is COP. COP is it provides the insight into the system's overall efficiencies and energy efficiency, reflecting the ratio of refrigeration capacity to motive steam used. So advantages of steam jet refrigeration: it is simple in construction. The system is simple and rigidly designed, making it easy to construct and maintain. So low vibration and low vibration free operation. Since pumps are the only moving parts, there is a minimal vibration during operation. Low maintenance cost. The system design involves fewer moving parts, leading to how maintenance costs and high reliability and high refrigerating capacity. The system can handle large cooling capabilities, that is capacities up to 300 tons of refrigeration, making it suitable for various industrial applications. But it is very well suited for industrial applications. Safe for use, it uses water as refrigerant, which is non-toxic and non-flammable, and adaptability, the system can adjust to varying load conditions, providing flexibility in operation. Low running cost, the running cost of the system is relatively low. So disadvantages of steam jet refrigeration system: temperature limitations. This system is not suitable for temperatures below 4 degrees Celsius, making it unsuitable for some refrigeration applications and requires sub-zero cooling. So high maintenance of flash chamber. For efficient operations, the flash chamber must be maintained at low temperature, requiring continuous attention in providing chilled water. Energy and efficiency losses. So the significant energy losses may occur and efficiency is reduced due to a lower enthalpy at certain stages of the cycle. So we will see a problem here. The steam ejector refrigeration system is supplied with a motive steam of 7 bar saturated with water in the flash chamber at 4.5 degrees Celsius. The makeup water is supplied to the cooling system at 18 degrees Celsius and the condenser is operated at a pressure of 0.058 bar. The nozzle efficiency is 88%, the entrainment efficiency is 65%, and the compression efficiency is 92%. The quality of steam and water vapor at the mixing point is 92%. So now determine these following: mass of motive steam required per kg of flash water, and quality of water flashed from flash chamber, and refrigerating effects, so per kg of flash vapor. So mass of motive steam required per ton of refrigeration, and volume of vapor removed from the flash chamber per ton of refrigeration, and coefficient of performance. So that is the performance measure of any refrigeration system. So COP should be find out. So this is the given data. Motive steam is 7 bar pressure saturated steam, and flash chamber temperature is 4.5 degrees Celsius. Makeup water temperature is 18 degrees Celsius, and condenser pressure is 0.058 bar, and nozzle efficiency is 88%. So that is 0.88. So entrainment efficiency is 65%. So that is NE, that is equal to 0.65. And quality of steam at the mixing point is 92%, so x equal to 0.92. So mass of motive steam per kg of flash vapor. So enthalpy and quality of motive steam from steam tables of 7 bar saturated steam. So first you have to find out all these parameters from steam tables TS diagram. So HA equal to 2762 kilojoules per kg. Enthalpy of steam is at 7 bar. So HF equal to from enthalpy to saturated liquid. So that is 1862 to 2.16 kilojoules per kg. And the nozzle efficiency formula is equal to efficiency is equal to HA minus HG divided by HA minus HB. The actual enthalpy drop, so that is HA, and HB is enthalpy at the point where the steam enters flash chamber, and Hg is ideal enthalpy drop which corresponds to isentropic process, and using the nozzle efficiency we can calculate Hb and Hg, and Hb equal to Ha minus the efficiency into Ha minus Hf. Substituting all these values, so that is we have nozzle efficiency is 88%, so 2762, that is Ha minus 0.88 into 2762 minus 1862.16. So Hb is 1970.14, that is kilojoules per kg. So entrainment efficiency, the quantity of steam at the mixing point is 92%, which means the dryness fraction Hb at the mixing point is equal to Xb equal to 0.92, and the enthalpy of mixer, the enthalpy at the mixing point Hm, so at the end of the nozzle is Hm equal to Hf into Xb into Hfg, and where HFG is the latent heat of vaporization from the steam tables for the temperature 4.5 degrees Celsius. And HFG we can find from steam tables, and HM we can find from steam tables. And quality of water flashed from flash chamber is equal to decrease, that is dryness fraction calculation. The enthalpy of the water flashed from the flash chamber is given by the steam tables at value at 4.5 degree Celsius. HF equal to 1862.16 kilojoules per kg. The quality of water flashed from the chamber can be found using the formula. So XF equal to HM minus HF divided by HFG, that is equal to 0.68. So refrigerating effect per kg of flash vapor. So here the refrigerating effect is the difference between the enthalpy of the water entering the flash chamber and the enthalpy of flash chamber. So Rg equal to Ha minus Hb, so that we are getting 791.86 kilojoules per kg. And mass of motive steam required per ton of refrigeration is the to calculate the mass of motive steam required per ton of refrigeration, we use the refrigerating effect per kg and the total refrigerating effect per ton. So that is equal to 1 ton of refrigeration. In terms of kilowatts, it is 3.517 kilowatts. So that is kilojoules per kg. So we can find this M motive steam. So that is in terms of Hc minus Hr. So we know all these values. So substituting this, so Q equal to 1 only. It is 1 can be assumed, and the point that is equal to 7.98 kg of steam per tonnage of refrigeration. So volume of vapor removed from flash chamber per ton of refrigeration. So volume of vapor removed, the volume of vapor removed from the flash chamber can be calculated using this formula. So this is Vc equal to Q into Hc minus Hf divided by H of water, where H water, your vapor, is the enthalpy of saturated water at 4.5 degrees Celsius. Using steam tables we found, so that is Vc equal to 782 meter cube per tonnage of refrigeration. And the coefficient of performance of the system, the coefficient of performance of the system is the ratio of refrigerating effect to the motive steam energy consumption. So that is COP equal to M motive steam into Hc minus Hf Hr. So divided by M motive steam equal to X into Ha minus Hb. So by substituting all these values, so COP can be find out. So that is coming around 0.586. So COP is very lesser. We have to see the final answers. And the mass of motive steam required per kg of flash vapor, so that is equal to 1.523 kg per kilojoules per kg. And quality of water flashed from the flash chamber is equal to 0.96. So refrigerating effect per kg of flash vapor is equal to 701.86 kilojoules per kg. So refrigerating effect per kg of flash vapor, so 791.86. And mass of motive steam required per ton of refrigeration, so this also we found out. So that is 7.98 kg per tonnage of refrigeration. So the volume of vapor removed from the flash chamber per ton of refrigeration equal to 782 meter cube per tonnage of refrigeration. So the coefficient of performance is 0.8586. So this is another parameter we have to determine from this particular problem. So next problem, a thermal power plant of 2200 kilowatt capacity is supplied with steam from the boiler at 30 bar and 400 degrees Celsius. A refrigeration load of 150 tons is taken by a steam jet refrigeration system. The To operate this system, steam is bled off from the steam turbine at 5 bar. The vacuum maintained in the condenser is 730 millimeter of Hg. The steam enters the flash chamber at 18 degrees Celsius. The various efficiencies of the system are as follows. Isentropic efficiency of the steam turbine is 90 percentage, and nozzle efficiency is 90 percentage, and entrainment efficiency is 65 percentage, and compression efficiency is 65 percentage, and all are very less compared to isentropic efficiency. It is 90 percentage, nozzle efficiency it is 90 percentage. So using the Mollier diagram, determine the following: dryness fraction of the steam leaving the flash chamber, mass of motive steam that is held off from the steam turbine, the mass of steam generated in the boiler, and mass of additional steam to be generated by the boiler due to refrigeration load. Coefficient of performance of the system. So this is the complete picture. Now this is the flash chamber, and a pump is provided through nozzle. This is nozzle and a thermocompressor, and we have this line you can follow thermocompressor, and from here it is condenser is receiving. Again from condenser it is go back to tank, and from condensate safe pump, and from here we have to start the process. So it is a cyclic process. The corresponding TS diagram is shown like this. So for this problem, all the values we have to draw like this. For 400 degree Celsius and for 30 bar, it is 5 bar saturation curve. So this is 0.4 bar and 0.1 bar. So the dryness fraction of steam leaving the flash chamber, using the Mollier diagram, analyze the process where steam is bled off from the turbine at 5 bar to the flash chamber. So from the Mollier diagram, so we can see the Mollier diagram, the steam tables. It is a like chart. You can refer that. Please refer it, and also you should carry that to all exams. And enthalpy at point 1 before steam enters flash chamber. So that is 3232 kilojoules per kg at 30 bar and 400 degree Celsius. Enthalpy at point 2 after expansion to 5 bar, so that is equal to 2792 kilojoules per kg, and the process 2 to 3 shows the isentropic expansion in the turbine, and isentropic efficiency formula. So turbine efficiency equal to actual enthalpy drop divided by isentropic enthalpy drop, so that is equal to H1 minus H2 divided by H1 minus H3. So this is the dryness fraction of the steam leaving the flash chamber. So substituting these values in the Mollier diagram, so H2 equal to 2816.16 kilojoules per kg. So the remaining steam expands in the turbine from 5 bar to 0.04 bar, and we can now find the dryness fraction at this point in flash chamber. From the Mollier diagram, the dryness fraction of steam leaving the flash chamber is calculated here. So then mass of motive steam bled off from the steam turbine. This also we need to determine here as second step. So using the nozzle efficiency, and enthalpy values, the nozzle efficiency equation is, so that is nozzle efficiency equal to HA minus HG divided by HA minus HB, and you substitute all these values. So HA already we know, and HB equal to 1968 kilojoules per kg, and HB equal to 2115 kilojoules per kg. Enthalpy of expansion to 0.04 bar, and substituting these values into the nozzle efficiency formula. So 0.9 equal to, only Hg is unknown, so 0.9 is the nozzle efficiency. So now this unknown can be find out. So Hg comes as 1968 kilojoules per kg. So this is the answer for step 2. So we can convert this mass of motive steam bled off from the steam turbine can be calculated. So that is M motive equal to 810 kilojoules per hour, that is kg per hour. So coming to next step, so mass of steam generated in the boiler. So the mass of steam generated in the boiler can be determined by using the energy balance equation. So that is M boiler equal to M motive plus additional steam required. So from energy balance, we find that mass of steam generated in the boiler is M boiler equal to 972 kg per hour, and the mass of additional steam to be generated by the boiler due to refrigeration load. So the additional steam required to handle the refrigeration load is calculated using the difference between the cooling effect and the steam used in the turbine. So that is mechanical additional is equal to 604 kg per hour. So next step, fifth step, to find out COP. The COP is calculated as the ratio of refrigerating effect to the energy used in the system. So COP equal to 150 into 210 into 60 divided by 972 into 2714.6. So after solving this, we are getting COP that is equal to 0.716. So final answers I am listing down here. You can also list down like that, and where we are completing the steam jet refrigeration system, and in next we will start the thermoelectric type of refrigeration system. So there ends this topic. You can refer the Rajput or Kurmi for this particular topic, and remaining all are same like earlier. So e-resources also there, you can refer e-resources also. So thank you students, we stop here, we will meet again in next session.